For the second talk today, we have Scott Balchin from Queen's University, Belfast, who will tell us about computing something with n-infinity operads.
Yeah, so thank you. Um, so the first thing I mentioned is they are testing the fire alarm here at some point in the next hour. I don't know when. I will jump out my seat when it happens, but it'll be fine. So yeah, I'm gonna attempt to talk about some algorithms and some ideas about computing n-infinity operads. I'm going to start with some motivation for those of you who've not seen it before. I'll then discuss the algorithms, and I'm going to do what you should never do during a talk, and that's live demo some code. Um, what could possibly go wrong? So yeah, we'll see how that goes. So I want to start by talking about the motivation, so kind of the math between it. But the idea is really to kind of put the E and C in eCHT today. So start with some motivation. So it kind of begins with if I have X, a spectrum or space, I mean, whatever takes your fancy, then homotopy commutativity asks when a multiplication M, so x cross x to x, um, has the property. So it's just the usual diagram. I have x cross x. I could twist my entries, and I can compute M in either of these cases. And it's an x, and we ask that this commutes up to homotopy. So this is obviously very classical and pretty well understood at this point. And the idea, of course, is that we encode this data via e-infinity operads. So today I've chosen to not kind of go over what operads are and e-infinity operads, so I can kind of beeline to the fun. But yeah, so this is all to do with e-infinity operads. So of course, if I'm asking for a homotopy on this triangle, I need to record kind of homotops between homotopies. If I have three inputs and I'm twisting them around, so I have this infinite collection of data, which gives me an infinite collection of spaces, ON, which assemble into an operad, and homotopy commutativity is controlled by these e-infinity operads, and in particular, we say that X is homotopy commutative. If it is an algebra for an e-infinity operad. And again, I'm not going to go into the technicalities of this today, but basically it says you have your spectrum or your space X, and it has this structure, this operad on it that allows me to control these equivariant and equivariant homotopy commutativity structures. Okay, and you'll notice I've written an e-infinity operad. We have a few different choices for this. Things like the Barrett-Eccles operad is an e-infinity operad. Little infinity disks is an e-infinity operad. And if you've not seen this before, this might make you feel uneasy. So note many different models for e-infinity operads. But their categories of algebra are all equivalent. So, but they're so that's fine. I mean, it doesn't matter which infinity operad I take. If I look at algebras over the infinity operad, it's the same as had I picked any other model. So there's kind of no choice. Very classical story. Um, but what happens when we introduce the action of a finite group G? So throughout my talk today, so G is going to be a finite group. So pick your favorite group. And G is now going to act on my object X. So we're really maybe thinking about category of G spectra. I want maybe orthogonal G spectra, so I have a nice nodal product and all that jazz. And again, we want to encode this idea of there being a multiplication on my spectrum and it being commutative up to some sense. So You might have, for example, heard of things like naive commutative ring spectra and genuine commutative ring spectra. So these all kind of fall under this guise. Um, and, one way to think about this is how much of G do I care about? We'll see eventually that kind of this naive thing doesn't really care about the group G. But if you're genuine commutative, then you really care about the group G. And what we're going to see is there's a whole kind of land of things in between, and that's where this talk's going to be situated today. So here's the bug slash feature of equivariant homotopy. We want to work with G operads, so operads with a G action. That's the sensible thing to do if you're looking at objects with G action. So I have G operads. And the thing is there are many G operads whose underlying non-equivariant thing is E infinity, right? So non-equivariant, they're just E infinity. But they have inequivalent categories of algebras. So this is you might call it a bug, but it's really a feature. And it comes down to this kind of difference between naive and genuine in the following sense. So here's an example. So to define an operad, I need to define a sequence of G spaces for all n. So let me say that En is just going to be classifying space of sigma n, and I'll equip it with the trivial G action. Or I could take this other one, Eg of n, and this space is going to be a universal space for G cross sigma n bundles in G spaces. And it's not hard to convince yourself that the underlying non-equivariant object in both cases is just an E infinity operad. But the problem is algebras over E, let's say in G spectra, is inequivalent to algebras over EG. So then the question you might ask yourself is how many different geoparads, let's say E with kind of inequivalent categories of algebras. And of course, by E, I mean which non-equivariantly are E infinity. So it's a natural thing to ask. We know that there's kind of this thing at the top, which is the genuine commutative ring spectrum. This is EG. There's a thing at the bottom, which encodes naive commutativity, this EN here. And, it's a perfectly natural thing to ask, is there anything in the middle? Like, is that the best and worst case? Another way you might think about this, so also, if X is a genuine commutative ring spectrum, and L is some Basford localization of G spectra, then you can tell. So this is kind of calculations of Hill, Hopkins, and some other people. So L of X. So I applied the Basford localization to my genuine commutative ring spectrum X. This need not be genuine commutative anymore. But it is always naive commutative. So it's the same story, right? We start with something that's genuinely commutative. We're going to localize it. We know it might not be genuinely commutative anymore. It's always going to be naive commutative. But you say, is it at least something close to being genuinely commutative, or is it really bad? So this is the idea. We kind of want to trawl the space between naive commutative and genuine commutative. Okay, so this was thought about by Blumberg and Hill, and they came up with the following definition. So an n infinity operad is a G operad such that. So the first condition is that the zeroth space is G contractible. Second condition is the action of sigma n. So if I'm talking about symmetric operads, so I have a sigma n action on ON is free. So this is exactly the same as you have for an E infinity operad. You ask that sigma n acts freely. And then the third one is this kind of funky condition. So ON is a universal space for a family of subgroups of G cross sigma n containing all subgroups. The form H cross. Okay, so this is the definition of an infinity operad, and it solves the problem that I mentioned. So this does classify kind of what happens in between these two extremes. And there's some pretty neat facts about these things. So again, Lundberg and Hill proved these things. So the underlying operad, so non-equivariant operad of an infinity operad is an E infinity operad. So it is exactly what we're talking about. We have these different G operads, which we get down to E infinity operads. The second condition is, well, the fact is that weakly equivalent. So they equip the collection of G operads with a model structure, and you can look at weakly equivalent N infinity operads. So weakly equivalent N infinity operads have equivalent algebras. So that's good. It's just like the E infinity case. And then kind of the surprising fact was the following. So I can look at the homotopy category of N infinity operads for G. So I said that there is notion of weak equivalences, so I can take a localization and form the homotopy category. This is a finite poset, which is pretty cool. So at the top here, we have what I called EG. At the bottom, I have E. And it tells us that there's some sort of collection of things in here. And I think it's a very natural question to ask what happens in here. You know, can we say something about this collection? How simple is it? How big is it? Has this poster got any structure? So this is where the story begins, really. So what we're interested in is computing this poset of the homotopy of n infinity operads. That's kind of a problem that quite a few of us have been working on recently. Um, so let me talk about how you might go about this. So let's move into kind of section two and talk about algorithms. Now, the first thing you'll note is the definition of an infinity operads. Yeah, it doesn't look overly friendly. But thankfully, due to the work of quite a few people, we have a much more combinatorial handle on this. So let me introduce a new structure. So as always, G a finite group. So a transfer system is a collection of, and we call them norm maps. And it's because, if you unravel it back to the equivariant story, I mean, they are generally the norm maps that appear in kind of HHR and things like this. So it's a collection T, and I'll denote them like this. So NKH, so where K is some subgroup of H, which is subgroup G. So I have this collection of norm maps, and it has to satisfy some properties. So one is identities. So this asks that just the norm map from H to H is in T for all H subgroup of G. The second one is about conjugation. So this asks if NKH is in T, then I get N. So I can conjugate both subgroups by the same group element, and this also has to be in T, so we close under conjugation, obviously for all G and G. 3 we call restriction. So this asks if NKH is in T, then I get this condition. So I take K intersect L to L in T. And what is L? L is just a subgroup of H. So I range over all subgroups of H, and I have to add in these objects as well. And then the final one is closure under composition, or transitivity, whatever you want to call it. So if NKH and NLK are in T, this asks that NLH is in T. Okay, so I just have these 4 rules. And the theorem that drives all of this is the following. So I should attribute this to a lot of people. So I'm just going to write down initials. So Blumberg-Hill did a lot of the heavy lifting. And then Rubin, Gutierrez, and White, Bonventure and Piera, and then myself, Barnes, and Reutzheim. I mean, we all kind of had smaller pieces in this, but Blumberg-Hill did the main bulk of the work, and then these 3 groups kind of independently proved a part of it, which was kind of the key. And what is the theorem is there's an equivalence of categories between the homotopy category of n-infinity operads and the collection of transfer systems ordered under inclusion, right? So I think if you look at the definition of a transfer system, this starts to look far more approachable than the definition of an n-infinity operad. So if we unwrap what this means, well, I need to tell you basically which norm maps are in my transfer system, right? That's all it is. So which norm maps are in there. So the kind of the takeaway here is that defining a transfer system is nothing more than determining which NHK are in T. And the way you should think about this is you take sub G, so the subgroup lattice of G, and what you're looking at is subgraphs. So subgraphs of sub G. This is how you should think about it. So you take sub G, so a collection of subgroups in order of inclusion. And if there's an inclusion from H to K, this could potentially be a norm map which you switch on or off. Right? So let's give an example of how this actually looks. because it makes far more sense than an example. So G is CP squared. Pick your favorite prime. Then sub G, well, we all know this one is E CP CP squared. And the choices I have is I could have a norm map from E to CP. I could have a norm map from CP to CP squared, or I have the norm map here. So I have three options. So in total, there's 2 to the 3 kind of potentials, right? I just range over all norm maps. I turn them on and off individually. So 2 to the number of intervals. So 8 potentials, but how many of these are actually transfer systems? So let me draw them down for you. So I'll use the same as up here. So I always have the empty transfer system. This corresponds to naive commutativity. I always have the full transfer system, which corresponds to genuine commutativity. And the whole point of the story is there's flesh in the middle, right? So T3, I could have this one. I could just have the norm from E to CP, but then not know anything about CP squared. This is a valid transfer system. So T4, I can do the same, but I just have from CP to CP squared. I have a fifth one. So let me do it this way. So I'm going to start by drawing this long norm here. So this is the norm from E to CP squared. But by the restriction rule, so CP is a subgroup of CP squared. So by the restriction, this implies that you also have n of E intersects CP to CP. Yeah, so it forces this arrow here. And actually, this is it. So you can check the other combinations and they all fail the axioms. For example, if I try to do something like this, then this fails composition. Because I have a norm map from E to CP and from CP to CP squared, but I haven't given the long composite. So this is not valid. So in totality, we see that the number of transfer systems or n infinity operads up to homotopy in CP squared is just 5. So there was 8 possibilities, only 5 of them work. And actually, you can prove, so this was myself, Dave Barnes, and Constanze Reutzheim, that if you look at CP to the n, then the number of n infinity operads up to homotopy is just the n plus first Catalan number. And, we even prove that the poset structure is that of the icosahedron. So, somehow this is quite nice and promising. But you might be surprised. So here's a remark. We only have counts for the family CP to the n, for the family CP squared, and CP squared Q and DP to the n. Oh, this should be an n there. P is not 2 in the final example. So we very quickly made progress with CP to the n, with the icosahedron. We're very happy. And then it just gets really hard really quickly. And I want to show you why it gets hard quickly. Why is this actually an intricate problem? So there's two things I want to point out. So the question is, why is it tricky? And I want to give you 2 reasons. So the first reason, let me look at G is CPQ, where P and Q are distinct primes. So let me just draw down the transfer systems for this. Should be able to use the wonders of technology to speed this up. Okay, perfect. Okay, let me just box these up. And like the spoiler is I've already drawn as many boxes as I need, but there we go. So there's the empty one. I could have this one, which is everything. Okay, I can have just this. So I should, this is E, maybe CP, CQ, CPQ. I have this one. I have this one. Watch me forget them now. I have this one. I have this one. And I have this one. And then I have this one here. Um, this one here is problematic. Why? Well, you might hope that for CPQ, I can infer everything just by knowing what happens in CP, what happens in CQ, and doing certain manipulations on these, right? So if I look at what I have here, like with this one here, I've just taken a transfer for CP. This one is I've taken a transfer for CP and a transfer for CP. This one also happens quite nicely. But in this final one here, this long diagonal, you can't get from any sort of guessing or shoving around the CP CQ story. So what I'm trying to say in not so many words is we aren't lucky enough, or maybe is lucky because it means there's work to be done, to have things like product formulas. Right? So even for CPQ, you have to work very hard to get what you want. You can't just say, well, I know it for CP, I know it for CQ, and I just do some amalgamated sum that just doesn't work. And then the second is that we can't work up to conjugacy. Um, what do I mean by this? Well, we've seen in the definition of a transfer system here that I have to be closed under conjugacy. So you might just say, well, why don't I work up with subgroups up to conjugacy and just do it with that? And the point is it actually doesn't work. So for S4, there's 3 copies of the Klein 4 group living in 3 copies of D4. But each Klein 4 group only lives in 1 copy of D4, and you have to actually remember which copy lives in what. Um, you can convince yourself this is true. So in particular, I can't just work up to conjugacy. You have to actually work with the full subgroup lattice. Why is this a problem? Well, let's think. If we do a naive check, so I just look at all possible norm maps, I turn them on and off in turn, and I say, is this a transfer system? Is this a transfer system? So if we do a naive check, we have 2 to the k checks to do, where k is the number of non-trivial intervals, non-trivial intervals, so h less than k, right? It's enough to know which non-trivial ones are in there. If you do it naively, there's 2 to the k things to do, and you say, okay, that can't be that bad. So if G is S4, you say, well, what's K there? K is 120, so you're looking about 10 to the 36 things to check. And like I'm sure we can all appreciate that's a big number, and computers aren't really designed to deal with that many things at once. That's not something you want to invest your time in, right? Especially by hand. So this annoyed me a lot. So I think this time last year, I knew I was going to be having a bit of time off work, and I wanted something to do in my downtime. Not like I didn't want to do anything too technical. So it's like I'm going to try and work out transfer systems for S4 because I know what fun is. But you immediately see that this isn't going to work, right? 2 to the 120 is just gigantic. So you need to be clever. Um, and just to know, I mean, 2 to the k is usually so much bigger than the number of transfer systems for G. I mean, so for S4, we'll see that we number of transfer systems is about 10 to the 4, not 10 to the 36. So you really have to be clever to get this to work. So how do we be clever about this? So that here's the first algorithm, and this was given to us by Rubin in the appendix of one of his papers. And what he does is he says if R, so this is collection of norm maps, then so it's not necessarily a transfer system. I'm just taking an arbitrary collection of norm maps. So what does he do? So step one is you let R naught be R. Step two is you close under conjugation. So, I add in N, G, K, G inverse, G, H, G inverse if um, N, K, H is in R. So for any element that's in R, I just add all possible conjugates. Then two is I close, so R1 is this. I'm making a meal of this, aren't I? R2 is we close R1 under the restriction axiom. So I go through each norm map and I say just add all of its restrictions, add everything that's possibly restricted from it. And then four, so R3 is I then close under composition. And doing this in practice is actually a bit tricky because you can imagine I could have something like this. I could have this norm, and this norm. And if you actually want to do this, I mean, you might close this under composition, and then you have to go again and close this under composition. This is from a purely computational viewpoint of how this works. You do have to be careful with closing under composition. This confused me for a while. So what did Rubin prove? Then R3, which I'll just call angle brackets R, is the smallest transfer system containing R. Okay, so this is nice. I can take any collection of norm maps and I can generate the smallest transfer system containing R. I mean, this works for multiple reasons. I mean, we knew abstractly this worked because the collection of transfer systems is a lattice, so it has a complete lattice, so it has meets. So, we can use the meet to generate this essentially, but this explicit algorithm of just adding in norm maps is very helpful. Why is it helpful? So let me take a 360 definition. A closure operator on a set S is a function, so I'll call it CL from the power set of S to the power set of S, such that X is contained in its closure. If X is contained in Y, then the closure of X is contained in the closure of Y. And then secondly, the closure of X is just the closure of X, so it's idempotent. Closure from topology or any other of the 50 other times you've seen a closure operator. So X is closed if CLX is X. So it's something that we've seen so many times in math. And the point is, and I'll tell you why it's important in a second. So the point is that Rubin's algorithm is a closure operator. So curly brackets. So it goes from the power set of the intervals of the subgroup lattice. to itself. So the power set of intervals of the subgroup lattice with closed sets, the transfer systems. Okay, so I've just taken Rubin's algorithm, I've cast it in another language. It's a closure operator, and the closed set's this closure operator in the transfer systems. So why is this important? So the key point is there are really good algorithms for computing closed sets, like really good algorithms. So the computer scientists back in the 90s, they used closure operators for certain database operations. So back in the 90s, they were already designing really efficient parallel algorithms that could find closed sets of certain closure operators. So what you do is you go online, you find one of these algorithms and you implement it. So if you can implement that along with Rubin's algorithm for a group G, you suddenly have an extremely efficient algorithm for computing transfer systems. Not fire alarm test. Okay. Let me give you a very, very brief idea of how the algorithm works before I give some quick examples because I realize I'm running out of time. So how does it work? So you start with looking at the closure of the empty set, right? So I'm going to do this for CPQ, let's say. So this is just the empty transfer system. Okay. Then step one is for each H to K in the intervals of sub G. So for each non-trivial interval, we do the following. So I take what I have, I union it with NKH, and then I take its closure again. Do I still have? No, okay. So in this case, we only have 5 different edges, so this results in 5 things. Okay, so I have this, I have this, I have this one. The closure of this is this. I have this one, the closure is this, and I have this one. Okay. So this is the first step of the algorithm complete. Then what the second step does is it takes each one of these and repeats the algorithm. So now instead of doing empty set, I would do this union sum nkh, and I take the closure of this. Okay, and then what I do is when I see new stuff, I record that, and that becomes my new set of things that I check the next time I run the algorithm. And once you don't find anything new, you can prove you found everything. So this is how this works. So it's very far from being exhaustive search. In the CPQ case, it looks like this looks like it's going to be work, but this algorithm is fantastic for large groups. So I'm going to stop sharing my iPad. I'm going to share my other screen, hopefully, and we're going to see if we can run some examples and see how effective this code is, which means it's about to go horribly wrong. Um, Desktop 2. Can everyone see some Sage code? Yes. Okay, so let's think about the steps here. So if I want to implement this, I first of all need to choose my poison. So for me, it's Sage and C++. I need to implement how to store group data. I need to then implement Rubin's algorithm and then implement an algorithm that finds closed sets. These are the steps you have to undertake. So what I did is this is Sage code. So some of you are hopefully familiar with Sage. I don't want to go over how it's implemented. I can happy to talk about that afterwards. So what this does is up here, you just pick your group. So right now, this is taking the prime 30, our favorite prime. It's looking at the cyclic group of order P, and then it's doing one copy of this. So G is just C30 here. You'll notice that I can do loads of other groups. I can do gap small group notation. So I can take any small group and this works. And this makes a file, CPQR, right? Because 30 is CPQR. So I'm going to run my Sage code. So that's it run. And what did it do? It's made me a C++ file because of course it did. Let me talk you through what's happening here. So these are the subgroups of C30. I think we can all agree with that. So this is the lattice of subgroups. The way to read this is group 0, so 1, is included in group 3, C5, and so on. So the fourth thing in the list, because I index from 0, is included in the sixth thing. So this single vector here encodes the entirety of the subgroup, lattice of subgroups. Okay? So I've done this because I don't want to run combinatorial problems in Sage because Sage is not good at doing that. Like, have you ever tried to throw Python a load of combinatorial stuff? I mean, it just gives up, right? Python is not designed to do mass computation like that. Now, here's where it gets interesting. So with Rubin's algorithm, I have to close under conjugacy, I have to close under restrictions, and I have to close under composites. And what you do is you store all of that data before you even begin. So I'm not going to go through all of this. So the conjugates is boring. Let's move to S3. Get some conjugates then. So now this should be read as the following. So 0 corresponds to this norm map. So all of these are potential norm maps, right? So norm map 0, so that's the inclusion of this subgroup into this subgroup. If I look at all possible conjugates of it, this norm map conjugates to the 0th one, so itself. It conjugates to this one, and it conjugates to this one. So I store all the information about the conjugates. I kind of hard store this, which speeds up computation because I can tell Sage, output this file, and I never have to worry about the fact to have a group again because it's all just stored. So that's great. Lookups are really fantastic. What's not so great is let's look at my file for S5. My laptop is going to lag while it opens this. So this is a 10 megabyte file of just information about S5. I have the same one for A6. So the A6 file is 140 megabytes. So we're talking like 100 floppy disks worth of data to store what I need about A6, but that's fine. Okay, so that's what happens. So I have Sage code, which knows about groups and it extracts all the information into here. And then here's my main code. I don't really want to talk about any of this. This is highly parallelized. So here's the file we just made. So CPQ. Let me run this. So CPQR, sorry, is what we just did. So it's telling me there's 450 transfer systems for CPQR, which is true. We proved this by hand a long time ago. So at the 0th algorithm step, it finds one transfer system, and then it has two transfer systems, 20, then 119. Here at step 3, this is where the complete transfer system, where with all norm maps appears. So the number 3 is also the number of maximal subgroups of that group. This is not a coincidence. The really interesting number is this one. I have to go up to 7 steps in my algorithm to find all transfer systems. Question, I pick a group G. How many iterations of the algorithm do I need to do before I find everything? Right? So this is a question I'm thinking about in great detail with Catherine Adamic, Miguel Barrero, Stephen Schreier, Noah Wisdom, and Valentina Zapata Castro. The combinatorics behind this are really intense, but it's nice to know this because, for example, I take C, P1, P2 up to PR, distinct primes. We know at what stage the algorithm is going to terminate. And a lower bound for the number of transfer systems is 2 to that number, which means I know what the number is for C, P1, P2 up to P5. This number is 51. 2 to the 51 is far more transfer systems than we can ever hope to find with the computer. So that's a good idea to give up there and then, right? Now, so this is code which compute transfer systems. You can obviously add to this and start computing compatible pairs for incomplete Tambara functors or bi-incomplete Tambara functors. We can do things like linear isometries. We can count those, so the saturated and co-saturated. Once you have all the transfer systems, you can go a long way with this. And then the last thing I want to say is kind of the crowning achievement of all of this. So I wanted to set out and do S4, right? That was my thing, and we said that there was at most like 2 to the 210 transfer systems. Um, so there's 8,691 transfer systems. That's it. Conjugation does a lot of heavy lifting here. And then two more things, and then I'll stop talking. So I just want to run A5 for a minute. A5, pretty big group. I think we can all agree with that. There's only 987 transfer systems. What I want to point out, which is an interesting curiosity, there's only a singular transfer system that needs to go to step A singular one. There are loads of groups that have this property. I don't know why. I think it's very interesting. And then the final thing is I have managed to do S5. I ran this on, so Queens has access to high performance computing suites. So I ran this for, I think it took 10 days. I think it used 2 terabytes of RAM. And the answer is about 183 million. So you can see the growth of this is crazy. So I'm going to stop talking now. Thank you very much for listening.